Let's wait for 5 more minutes to other peoples to join, then we'll start the class. It's fine now? Okay. Good evening, everyone. This is me, Dorothy Sachdeva. So I guess it's already 6:05, so we should start today's class. Let me share my screen. Are you able to see the screen in the presentation mode?
Yes, madam.
Okay, thank you. So I'll begin with today's class. So this is the fifth lecture of Material Characterization course provided by Professor S. Sankaran from IIT Madras. And here am I, Dorothy Sachdeva, your PMRF TA. I am doing currently PhD at MRC department at ISC. So in last class we were discussing about the SEM. After the optical microscopy, we have started studying SEM, scanning electron microscopy, where the electron beam falls on the specimen. And in last class we discussed how the electron beam is generated, and after that we discussed there were different sources of electron gun, like the thermionic emission, field emission, and so on. And different sources have their different advantages. And then later on we studied how the electron travels from the vacuum column, starting from the electron gun toward the specimen, passing from different lenses. Like we had condenser lenses, we can have multiple condenser lenses, but as we told that the optical lens will be the one which will be just above the specimen. And then after that, these lenses are all the electromagnetic lenses. These electromagnetic lenses can change their focal length just by changing the current passing through them. So if we change the current passing through these lenses, then we can directly change the focal length. And for, like, for the case where we have the glass lens, where if this is the lens, it will have a specific focal length, for example at point this. But if we want to change the focal length of this, then we need to change the lens itself. But this is a very advantageous system in the electromagnetic lenses, where just by changing the current passing through the coils, these lenses are made up of copper coils. These copper coils are surrounded around the lens, and when the electron beam falls, and we can change the value of the current passing through these coils, so as a result the focal length will change, and as a result it can focus here or here, depending upon the current passing through the copper coils surrounding these electromagnetic lenses. So this is and to have these electromagnetic lenses and the electron beam, this whole thing is covered in that vacuum chamber. The vacuum chamber is around very less very high vacuum is there, less pressure of air is there, so that the electron beam follows the straight path starting from the electron gun to the specimen. Here in optic axis we were using horizontal as our optic axis, like our lens was placed here, and we were performing all the ray diagram using this as the optic axis and this as an object. But in this SEM we were considering the vertical line as the optic axis, where the electron beam also follows the the vertical path, where and where the convergence, where the ray diagram is not that this thing I guess I told multiple times in last lecture also. The ray diagram in this SEM will not indicate about the object and the image. It will indicate only about how the electron beam is getting reduced. In this case, we were doing the SEM part, we got to know that just a second, let me take one blank and do the in SCM. If this was our lens, this was the optic axis. In this, the ray diagram, the main aim of the lens is, like the condenser lens and the objective lens, the main aim of all these lenses is to reduce the probe size which is falling on the specimen. If this is your specimen, then we need to reduce the size of this to get the best resolution as much as possible, this size. So in this SEM we always used to do the demagnification of this probe. The ray diagram is not directly related to the object and image, it is relating to the probe size. So the probe we always need smaller, so in SEM we always use lenses to demagnify the probe. So there we never do magnification, we always do demagnification, so to reduce the probe size. Then different length after passing this these electron beam, after passing through different lenses, then reach the specimen. And then we briefly discussed that there will be some interaction volume which will be a pear shaped like interaction volume which will interact, which will be known as the interaction volume, and from there certain different energy of electrons and electrons with different energies will be released, and depending upon their energies there are various kind of electrons which are emitted out, and every time every electron will be emitted out, every kind of electron I mean will be emitted out, and depending upon the detector which you are using, suppose this is your specimen, your detectors, this is scanning, this is not transmitting. So scanning is done here like raster scanning, like point from this point to this point, and then again from this point to this point. So it will do a scanning. So this is known as raster scanning. So in this, the electron beam is not transmitted through the specimen. So it can be thick enough. It because the electron beam is only scanning on the specimen, and after the scanning it interacts with the specimen, and the electrons which comes out from this specimen, these go out, and depending upon the detectors which you are using, like the secondary electron detector is placed over here, this will be your secondary electron detector, and there are some backscattered electron detector which is a donut shaped kind of detector which is placed around the optic axis only. It is hollow, it is a donut shaped kind of thing. So this one is the back secondary electron, BSC. So the BSC electrons will be collected from by this detector, and the secondary electron will be collected by this detector. But there are multiple electrons like characteristic X-rays, the Auger electrons, the Bremsstrahlung electrons. There are various kind of electrons which are emitted, but they will be emitted every time. But depending upon the detector which you are using, you will get information based on the detector. So were there any doubt in last lecture, or everything was quite clear?
Madam, you are saying that the scanning was a raster scanning.
Is it a linear or? I'll just explain you once again. Let me draw a specimen. Suppose this is your specimen and these are your different points. Let me name them as A1. Someone is in the lobby, let me admit them. Yeah. This is point A1 followed by A2, A3 and A4, suppose. And here are also 4 points which are linear to A1, A2 only, which will be denoted as B1, B2, B3 and B4. Okay, so I am just saying that here it's done is raster scanning, RASTER. Raster scanning. So what does raster scanning mean? That it will scan the electron beam is coming like this. So it will scan starting from point A1, it will go to point B1, and then it will pull it up and come back to point A2. It will during while going from point A1 to B1, it is doing scanning, but while going from point B1 to A2, it is not doing any scanning. It will just pull up and come to A2, and then it will again start doing scanning. Then it will go to point B2, then it will do scanning, and then it will go back to point A3 without scanning, and then it will do scanning from point A3 to B3. Then it will go back to point A4 and do scanning from point A4 to B4 like this. This is known as the raster scanning. Like it will scan in, suppose this is your X direction and this is your Y direction. Then it will do scanning in X direction, then it will change its value in Y direction, and then it will do again scanning in X direction. So it is always doing scanning in the same direction only, and it is changing its position by going from point B1 to A2, B2 to A3, B3 to A4 like this. Got it? Is it clear now? Okay, okay. Any other doubt to anyone? I think the last lecture was clear. So now I will discuss about today lecture. Let me select the pointer. So last time we discussed about this interaction of electron beam with the specimen. So this is the incident high kilovolt electron beam which is falling on this specimen. Then some of the electrons are being absorbed by the specimen. Some are used to form the electron hole pairs, and some are directly transmitted through the specimen when the specimen is thin, and some will undergo the elastic scattering and some will undergo the inelastic scattering. Someone is in the lobby, I guess. Yeah. There will be also be the emission of the Bremsstrahlung X-rays, the visible light, the characteristics X-ray, the Auger electrons, and the majorly there will be we will study about this back secondary electrons and the secondary electrons. These last time we discussed that what does this back secondary electrons will signify and what does this secondary electron signify. What information will they give about the specimen? Can anybody tell me? Can anybody try? These were also included in the questions, also the practice quizzes and questions. What does information does the back secondary electrons and the secondary electrons give about the specimen? Hmm. Back secondary electron will, yeah. You are very good, correct. So this back secondary electron will be used when you need to get the Z contrast, that is atomic number contrast. Then these are the best electrons to have the imaging from these electrons, and the secondary electrons will be used when there is a rough specimen and you need to find the topography of the specimen. Then these secondary electrons are being used, and these characteristic X-rays are also being used when you people must have heard about the EDS, energy dispersive spectroscopy, X-ray energy dispersive spectroscopy, where you can directly image which element is present at which position. So these are done using this characteristic X-rays. So depending upon the different element, they have different value of the characteristic X-rays which are being emitted from the specimen, and even a single atom also have different characteristic X-rays, like from where the electron is being ejected. Is it from the very inner shell, or from the outer shell, or the electron is being transmitted firstly from the inner shell to outer shell, and then the outer shell is being emitted. So depending upon that which electron is being emitted, you can have different energy of electrons for a single atom as well. So today I'll firstly briefly tell you about the cross section, or the probability of an event the is given by, so this is a term Q, which is known as the events per incident particle per target size. So this is the probability of an event to occur, like the electrons which are following on the specimen. So they have certain probability that the event will occur. So that is given by this term Q, which is given by capital N divided by nt by ni, and its unit is centimeter square, where n is the number of events per unit volume, and nt is the target site per unit volume, and ni is the incident particles per unit area. So this is just the basic information, that there are certain possibilities that the event which you are need to tell what is the probability of that event to occur. So, and also I have a formula of the average distance, like traveled by an electron between two particular events, is given by this mean free path. This mean free path is very important for further classes and for further study also. So you just need to have a basic idea of what this mean free path means. So this is basically the average distance which is traveled by an electron beam between two events. Like if it is interacting, like if the electron is interacting to here and then to here, so the average distance, like from point here to point here, average distance traveled by an electron between two particular events is given by this mean free path, and this is given by lambda, which is given as a divided by n naught rho q, where A is the atomic weight, N naught is the Avogadro number, rho is the density, and Q is the cross section area. So the unit of this lambda will come into to be centimeter, and there will be, as we all know, that there won't be any single interaction of the electron beam with the specimen. There will be multiple events which will be happening inside the specimen. So the total lambda will be given by 1 by total is equal to 1 by lambda a plus 1 by lambda b plus 1 by lambda c, and so on. So this will be the reciprocal of each mean free path of each event. The sum of all those will give you the reciprocal of the total mean free path. And these things you need to keep in mind, that as the z will decrease, z means the atomic number, so as the atomic number will decrease, the lambda will increase. Why? Can you anyone tell me? Because, like, you can see, lambda will increase, that means the distance traveled by two electrons will increase, the z decreasing. At lower z there are less number of electrons, less repulsion is there between the incoming electron and the electron present inside the atom. So as a result, as z decreases, lambda will increase, and also as energy will increase, the lambda will increase, because the higher energy the electron is coming, it will interact much more. So the distance, so it will travel much faster, and it will have a less time to interact with the specimen. As a result, its lambda will also increase, because the faster electron will not interact much with the atom electron, it will just go without interacting much with the specimen. As a result, as the energy of electron will increase, the lambda will also increase. Is it fine? This mean free path is very important, and it will come as a important to understand the various concept further. So if you have any doubt in this mean free path, then do let me know. We will clear it right away. Otherwise, all other concepts are based on this mean free path. No hands are raised. I didn't hear any voice. I guess everyone is clear about this. Okay. So, as I told you, that as Z will decrease, the mean free path will increase. Suppose this is your carbon, this is iron, silver and uranium. So as you are going from here to here, your Z is increasing. Z is increasing means the number of electrons which are present in the atom itself is keep on increasing. So the incoming electron will be repelled by the electrons of the atom. So as a result, the more repulsion will be there between the incoming electron and the atom. So there the interaction volume will be much lesser as compared to the lower atomic number. So as a result, the lower atomic number like the carbon will have a much higher interaction volume as compared to the silver, uranium, which have a very high atomic number due to the electron repulsion. Also, there is one more thing which you can see from this figure, that at lower atomic number the interaction volume, like interaction volume is what? Basically the volume where the electron is being uh, interacting with the specimen. This is also given by some Monte Carlo simulations. There are some online softwares where you can do this Monte Carlo simulation, and you can find out that how the interaction of the electron beam with the specimen is taking place. And as I was saying, that there are one more thing which you need to keep in mind, that at lower atomic number like this carbon, this interaction volume will have a pear kind of shape, where firstly near the edge there will be a long neck kind of thing, followed by this interaction volume which is very big, whereas in higher atomic number there is no neck kind of thing. It will the neck kind of thing will be very small. It will be directly some spherical kind of thing which shows the indicates the interaction volume of the specimen. So here we got to know two things. Firstly, that as we will increase the atomic number, the interaction volume will decrease, and also the shape of interaction volume will change from pear shape to the spherical shape. And also the so these are two comparisons. Firstly, of this is at a constant energy, that is at 10 kilovolt for different elements. The this is tell about the number of events. The log, the y-axis says log sigma, which is the events per electron per atom per centimeter square. So as you are increasing the atomic number, the number of events, that is the, or someone is in the lobby. Yeah, so at a constant energy, when we are just increasing the atomic number, we can see that the probability of events to occur will be much higher in higher atomic number as compared to the lower atomic number. And also mm, just a second. Yeah, and when you have a constant atom and you just keep on increasing the energy of the incoming radiation, so as you increase the energy of incoming radiation, the probability of events to occur will decrease, because higher the energy, the less is the probability of for the events to occur, because higher energy electrons will directly away from the specimen without even interacting with it, as compared to the lower energy electrons. So these two graphs, I guess, must have been clear to you. This will tell you about how the atomic number is varying, how varying the atomic number will affect the number probability of events, that is crossing, and in this will tell you how changing the incoming electrons energy will affect the probability of an event to occur. Someone has unmuted themselves. You can raise your hand if you have any doubt. Yes, Shavin.
The first graph, there is a doubt. In the first graph, when there is a atomic number is less, interaction is showing less. Should be more, right?
This is the probability of an event to occur. The y-axis says the log of sigma, which is the number of events per electron per atom per centimeter square.
So the volume is coming more for carbon, right? So why volume is coming more? Because interaction must be more.
But the
But
initial,
graph shows that the interaction is less for
you can see
carbon.
from here you can see that it is having this spear shape, no? So it is
Yes.
firstly having this neck, so due to this neck region only, the eh, probability of an event, because most of the electrons will come from here only, so as a result the carbon will have a lesser probability of an event to occur as compared to the higher atomic number.
In a previous slide, can you go there? We have given a statement about energy and volume, atomic number and interaction volume.
This actually in the, can you see the PPT?
Yeah, in PPT I'm able to see this graph. I'm able to see in the previous slide. It showed that one statement is there. So just I want to go to that statement. Maybe I'm finding that there is contradiction.
Okay.
Yeah, decreases. No, Z decreases. Interaction lambda increases. Lambda increases means interaction is you say interaction will be less, right? Interaction will be less. But when interaction is less, why the volume is more?
This here in this graph, this y-axis is basically the s- is basically the probability of an event to occur, which basically is the how the scattering is taking place. There is one formula which is given as q, this log of sigma, sorry, I'll just write it properly. This log of sigma na, this y-axis is basically the scattering which is taking place, and it is given by this q,
Yeah, yeah, this is scattering and more scattering,
and
more
which is
volume.
directly proportional to z square divided by e square into cot square theta by 2. So this is basically the scattering formula, and also you can see from this x-axis also, x-axis is the theta. So as you increasing the theta, the value of this q, that is the scattering term, will decrease, and as you will increase the z, the q term will increase, and as you increase the energy of incoming electron, the scattering will decrease.
Okay, okay. Actually, this is theta.
Yeah, it's theta. It's
So
given
let's
like
say
this. Phi or
taking
theta, you can say. It's given over here. You can see this one.
can you tell me this significance of the neck region and the remaining region? What is the significance of neck region? Why the neck region is there in the lower carbon, lower atomic number, and the higher
There will
atomic
be
number?
less repulsion in the according to me, there will be less interaction for the low low atomic number. So as a result, electron will first pass on directly to the specimen, and after that it will have interaction with the specimen, so it will have this kind of interaction volume. And in the higher atomic number case, it will initially will have the repulsion from the electrons which are present in the specimen, so it will not have this neck kind of shape in this case, because it is repelling, starting repelling from the initial phase only. So as a result, it is having a small interaction volume, and it is also following this sphere kind of shape as compared to the pear shaped.
Yeah, yeah. Okay, thank you.
Is it clear to you now?
Yeah, it's clear. Thank you.
Okay. Any other doubt to anyone? I'm not hearing any hand raise or any doubt, so I will move. Like you can see in this one, these are the Monte Carlo. Let me take the pointer. So these are the Monte Carlo electron trajectory simulations of the interaction volume in iron at 20 kilo electron volt for various tilts. So this, the main purpose of this is to show how the tilting is happening. I just wanted to clear it to you that these Monte Carlo electron trajectory stimulations are being done, where you can also see that this is having a shape, sorry, so this is having a spherical shape kind of thing, which is given as the interaction volume of the specimen. So in this case, as you tilt, if there is zero tilting, it will be simple Monty, the simple interaction volume which we learned earlier. And as we increase the tilting of the specimen, the interaction volume will also be tilted, because the electron beam is now coming in this direction and your specimen is like this. So as a result, this dense part shows that much of the interactions are taking place here, and this shows that less interactions are being taking place here. So if we are tilting the specimen, no, and if we are doing again further tilting from 45 to 60, then more number of electrons are being ejected from the specimen as compared to zero tilt. From zero tilt, you can see that the electrons which are coming out from the specimen, no, they are very less as compared to the electrons which are coming after tilting the specimen, because after tilting, the electron needs to travel very less distance as compared to the zero tilt. I'll take the pen and then I'll explain this to you. Yeah. So when you have done the zero tilting, the electrons are going in all direction, and they are coming back. And for coming back, the electron need to have a theta difference of 90. Hmm? Initially it is going in downward let me erase this and make it clear. If the electron is coming in this direction, if it need to go out from the specimen in this direction, it need to have not 90, sorry, it need to have a 180-degree rotation in its direction. But if the specimen is tilted, now the electron is coming in this direction, and if it need to go out from the specimen, it need to have a this go to this direction. So now you can see that it need to change its direction very less as compared to the 0-degree tilt. And if we will decrease the tilting again, then it at 60-degree it need to change its direction much lesser as compared to 45-degree. So more number of electrons will be ejected at 60-degree tilt at higher degree tilts as compared to the lower degree tilts. So as we increase the tilting, the electrons coming from the specimen will also increase. As a result, the image will be brighter as compared to the 0-degree tilt. And this is basically the, where is my pointer? And this is basically the electron energy distribution, which is measured with the energy. And firstly, the back secondary electrons have a much lower energy as compared to the secondary electrons. So firstly, there is a very high peak which is given by the secondary electrons, and after that there is this high peak region which at a lower energy, which and that these electrons are known as the back secondary electrons. These back secondary electrons have a coefficient known as the backscattered coefficient, which is given by this neta, which is given as the number of backscattered electrons divided by the number of beam electrons. And the number of electrons will be related to the current. So neta, that is backscattered coefficient, neta will be given as I of BSc, that is current of back secondary electrons, divided by the current of the beam. And here I have shown three different comparisons where in the back secondary electron increases with increasing atomic number. As we all know that the back secondary electrons are directly give the information about the atomic number of the specimen. So as we increase the atomic number, the number of backscattered electron will increase. As a result, the neta will also increase. So we are going from lower atomic number to higher atomic number in x-axis, and in y-axis it's the back second scattered coefficient. So as we increasing atomic number, it's being increasing. And also there is one more thing which you need to keep in mind, that is at lower atomic numbers there is a higher difference between the two atoms, whereas at higher atomic numbers, if the atoms are much closer to each other, then you will not be able to detect, because the slope at lower atomic number is much higher. So the distance of this and this will be higher as compared to the two atoms which are already at higher atomic number. At higher atomic number, its slope is very less, so as a result the backscattered electron coefficient difference is also very less. And also the effect of electron beam energy, so it does not have any effect of electron beam current. So these different symbols like triangle, circle, diamond are given by the different different energy of the incoming electrons. So as you can see, the y-axis is the back second scattered coefficient neta, and x-axis is the atomic number. So as you are increasing the atomic number, the neta will increase, and as you are changing the current density, there is no specific change in the backscattered coefficient. So it does not depend upon the beam current for the neta. And also you can see that the back secondary electrons will, for different atomic number, will be given like this. Like at lower atomic number it will be lower, and at higher atomic number, like for carbon it's like this, and for aluminium it increases, for copper it's further increases, and it increases from silver to gold. So as we go from lower atomic number to higher atomic number, the back secondary electron will increase. These things should be clear to everyone. If there is any doubt, then please let me know. Otherwise, we'll move to next, secondary electrons. There is no hand raise, so let me move to the next slide, where before going to the secondary electrons, I'll just briefly tell you about this. Last time I guess we discussed about this elastic and inelastic scattering in last class. Yes, we discussed about it. And the smaller the angular events, the larger smaller angular events and larger angular events. So as we discussed in the tilting slide, that if we will increase the tilting, the more number of events will take place. And there is one more thing which you need to keep in mind, that is the when the electron beam is coming in this direction, and it is directly, and the electron is directly coming from the incident beam interaction to the specimen, then that electron will be known as the back secondary electron 1, where only the single scattering event has been taking place. Because if this is the incoming electron and this is the electron which is being ejected out and which is being captured by the BSC detector, so this will be the back secondary electron 1, because it has been coming out, it's coming out after only this one interaction with the specimen. Whereas if there are multiple scattering, because the if the beam is coming in this, like this is the electron, and it firstly interacts at this point, and then it's get reflected in this direction, then it will have multiple interactions with the specimen, and then it comes out to the detector, then it have undergone the multiple scatterings in the specimen itself, and that will be known as the back secondary electron 2. This back secondary electron 1 has need to change, need to come directly from the incoming radiation, whereas this BSC2 can have the multiple scatterings within the specimen itself, and then the electron is being emitted out. So this is the BSC2. And they, after looking at all this, can anybody tell me what will be the energy of comparison of BSC1 and BSC2? Which one will be of higher energy? Yeah, because it has been coming out after only one scattering, whereas BSC2 have lost a lot of energy while interacting with the other things in the specimen. As a result, BSC2 will have a lower energy as compared to BSC1. Then we'll see something about the secondary electrons. The secondary electrons are the electrons which have a energy less than 50 electron volt. This is a general definition for the back secondary electrons which is being used from the initial time of this SEM. They, but their secondary electron detector will also have some amount of the back secondary electron, but it will not have much significance which can be observed in the image. So the back secondary electrons will have a certain uh, contribution to the secondary electron images, but it will not have some not experimental significance in the image. So these secondary electrons, as we all know, have a very lower energy. Someone is in the lobby or someone have a doubt? How many students are there? 10. Yes, Shalin.
My question is, suppose this band is pattern will come after multiple up and down, does it also
No, no. It the difference between the back secondary electrons and the secondary electrons are much. The energy difference is higher. The back secondary electrons will have higher energy as compared to these secondary electrons. Second, yeah, yeah, yeah. This the first statement, which is that the secondary electron energy is less than 50 electron volt. Now, this statement itself is very vague. There is no specific information provided for this statement. It is just a general statement that we generally consider the electrons which have less than 50 electron volt energy as the secondary electron. But there is no specific such energy term through which we can differentiate that this will be the secondary or this will be the back secondary electron. I told you in the last class also that this is just a vague statement only, but everyone is following this. There is no specific point, no specific energy term that after this energy, if the energy will be lower, it will be secondary electron, and after this is just a statement which we generally use to tell everyone that the secondary electrons are the one which have a lower energy as compared to BSC. That's all. Yes, yes. Yes. Okay. I guess I have a, yeah. We will discuss about this. Just wait for few more minutes. In the next slide it's there. Let me select the pointer. Yeah. So due to their low energy, they are very easy to collect because we will apply a small amount of positive potential and all these low energy electrons will be collected to the detector. So due to their low energy, they are easy to collect and come from a shallow depth. So give very high resolution. These secondary electrons come from a shallow depth, so they give a high resolution. And as the BSC has their coefficient, the secondary electron also has its coefficient, which is given by delta, which is the number of secondary electrons divided by the number of beam electrons, and which is given also be given by the current of the secondary electrons and the current of the beam current. So this is basically the comparison of delta and neta. The delta one is the back secondary electron coefficient, and delta neta is the back secondary electron coefficient, and delta is the secondary electron coefficients. So the y-axis tells both, and the x-axis is the atomic number. Why you people are joining so late? It's already 1 hour over. Please join on time so that you can understand. Yeah, so the secondary electron coefficients have this trend where they are not affected much by the atomic number, because x-axis is the atomic number, but the coefficient is not affecting by the atomic number. It is more or less constant only. But as we have seen earlier, that these back secondary electrons are very much affected by the atomic number. So as we increase the atomic number, the back secondary electron coefficient eta will keep on increasing, but the secondary electron coefficient delta remains more or less the same only. So these are some basic points which you need to keep in mind, that the secondary electrons are generated in the whole interaction volume of beam electrons in the specimen. Secondary electrons are generated in the whole interaction volume, but only those electrons which are within the mean escape distance from the surface are detected. So if this is your specimen, all the pink region starting from point this to point this is your specimen, and this yellow one is your dark yellow one is your electron beam. So when your electron beam is falling on the specimen, it is having this pear shaped, which is shown by this lime color. So after forming this after coming, the electrons will interact with the specimen and it will follow different kind of paths, and it will be getting deflected in different ways. So the electrons are coming in this direction, and the electrons which are being emitted directly from here, like which are shown by these lines. Let me choose the pen. So if the electrons are coming in this direction, let me change the color. Now red is already present in the figure. Blue, dark blue will be fine for the path of electron, I guess. So if the electrons are coming in this direction, then the electrons which are directly evolving from here will be known as the back secondary electrons, and the secondary electrons will be the one which will be coming from this region, and they are coming out. The second, sorry. But the secondary electrons will be generating in all of the interaction volume. The second statement says it will be generated in all the interaction volume, but only those in secondary electrons which are within this Z, this light pink region, because secondary electrons themselves have very low energy, and if they are coming from deeper down, then they will not be able to come out, because they will lose their energy and they will not be able to detect it. So but they are being generated in the whole interaction volume. So only the secondary electrons which are generated from this mean escape distance will be detected by the detector. As a result, this is the secondary electron escape depth. This Z1 is known as the secondary electron escape depth. The secondary electron are the one which are generated by the incident beam as it enters the specimen. Like the back secondary electron also have multiple kinds, like SC1, SC2, SC3, SC4. All kinds are there. For BSc we studied BSc1 and BSc2. BSc1 is the direct interaction of the incoming, and then it comes out as BSc2, and whereas BSc2 will be the after this multiple scattering, like all the path which is being shown in the red in this figure, if it will come out from here, it will be the back secondary electron 2. Whereas now we will see about the secondary electrons. Secondary electrons 1, SC1, are generated by the incident beam. So this is the incident beam, and the secondary electrons which are generated from this region will be known as SC1. And SC2 are the one which are generated by the BSc as they exit the specimen. So the BSC which is coming out, it can also have some secondary electrons. So these secondary electrons which are being generated by the back secondary electrons as they are exist exiting from the specimen. So these are the Se2 electrons, and Se3 are the one which are generated by the back secondary electron hitting the other parts in the chamber. Like this whole thing is present in a vacuum chamber. So if the back secondary electrons are hitting other parts, secondary electron can't hit because they have a lower energy, but these back secondary electrons can hit the other parts of the chamber, and if the other parts are now generating the secondary electrons, then that will be known as the Se3 electrons, whereas Se4 electrons will be the one which will be generated by the incident beam while hitting to the objective aperture before even hitting the specimen only. So before specimen there is objective lens which we all know, and we used to block the electron beam which are very away from the optic axis using this aperture kind of aperture. So if the incident beam is hitting this objective aperture and that is generating the secondary electrons before even hitting the specimen, then that will be known as the secondary electron 4, SC4 kinds. So there are different kinds of secondary electrons and back secondary electrons. Also, I'll briefly tell you about the Auger electrons and the characteristic X-rays. The Auger electrons are the one, for example, which have a very low energy, and it will tell you about the mostly about the surface only. They have very low energy. So if this is your incident photon, which, let me take the pointer only. So if this is your incident electron which is coming as a wave, and if this is interacting with the inertial electron, then the inertial electron is being emitted out. As a result, the electron which is present at higher shell will move towards the inner shell, and the energy difference of this movement from higher shell to lower shell will be very small, and it will generate these Auger electrons. Also there could be, if this vacancy is being generated in, if this is H, this is K, this is L shell, and if the K shell, the electron from L shell is being transmitted to the K shell, and after that the electron from the outermost shell is being transmitted to the inner shell, then that energy difference will also be generated, giving the Auger electrons. I heard some noise was there. Did someone have any doubt? Did someone raise their hand, or? I guess no. I heard that someone has raised their hand. Okay. So if the outer shell itself is transmitting the electrons to the inner shell electron, and then that energy difference will be emitted out, and that will be the Auger electrons. These Auger electrons have very low energy as compared to the incoming electron or all other electrons. This you know, no? If this is your K shell, L shell, M shell, and the incident electrons is emitting the K shell electron, then L shell electron is will jump from L shell to K shell. So this will have K alpha energy, and if the electron from M shell is getting jumped from M shell to K shell, then that will have uh, K beta kind of energy. So depending upon from where the electron is being jumped to the K shell, it will have different energies. but the energy of these Auger electrons are very less. Also, we have learnt in the previous slides that there are some characteristic X-rays which are being emitted from the specimen after the interaction with the electron beam. So if the incident electron beam is interacting with the K shell electron, then this hole is being generated. Then if the electron from the L shell is being transmitted to the K shell, then it will be known as the K alpha line. And if the electron from K beta is coming to the K hole present in the K shell, then it will be known as the K beta line. So depending upon the electron from where they are coming, they will have K alpha or K beta line, and they will have different kind of intensities, and each and every atom have different value of this K alpha and K beta, or we can have L alpha, L beta, like so on. So depending upon the atom present, if you have different kind of atoms, then you can check that the if you have selected the K alpha line for all, then you need to check that the specimen have different atoms, then that different atoms doesn't have overlap of the energy of the selected characteristic X-ray. Then you can change that only the K alpha line will be detected, the K beta line for this atomic number will be detected. Like that you can select, and depending upon that, if your specimen is having elements at different position, then you can directly image. Suppose this is your uh, gold and this is your palladium shell on the gold, then you can directly do the EDS mapping, and you can see that the gold will be shown here and the palladium or platinum I told no, so platinum will be here. So different atoms will have their different characteristic X-rays. These characteristic means that these are the characteristic of the atom from which they are being generated. Then I'll we will discuss about the depth of focus. I guess we have discussed about this depth of focus multiple times in optical microscopy as well as in the last class of the SCM. Like this thing, I guess most of thing are being covered in last lecture, I guess. So if this black one is your specimen and this yellow one is your incident beam, then if the incident beam is having a smaller spot size, the A1 has, suppose this is figure A and this is figure B. So figure A has a smaller spot size as compared to figure B. And also you can see that the smaller the spot size, the higher will be the resolution, because if the spot size is smaller, then it can detect multiple things which are present quite near in the specimen. So as a result, the resolution will be higher in this case. Also you can see that to have a smaller spot size, the alpha is basically the angle of the beam with the optic axis, like this one is the alpha. So when you are having smaller spot size, you will be having smaller alpha, and when you are having higher spot size, you will be having higher alpha. Also in last class, I remember we discussed about how the working distance will affect this alpha and how the resolution will be affected. Can anybody tell me that at higher working distance, the alpha will be smaller or higher, the spots or the spot size? At higher working distance, I'll just repeat my question, that at higher working distance basically means the distance of the detector with the uh, this your specimen. So as you increase the working distance, this. And as you increase the working distance, your alpha will be higher, your spot size will be higher, your resolution will be poor. I guess you told the opposite thing. Do you got it? Do you remember? We discussed this in the last class. The effect of working distance. The last two slides were there, no?
I think, madam, there is the optimum distance at which we get the high spot size, madam.
I'm just discussing how working distance will affect the spot size, and the spot size will be related to this depth of focus. This all these things are very intercorrelated to each other. Like the alpha is directly correlated to the spot size, and the alpha is also directly related to the working distance, and all these things as a result will give you how depth of focus will be there, how much depth of focus you can obtain of that specimen. What's your doubt? Between, like if this is your specimen, just a second. Yeah. So if this is sorry, so if this is your specimen, then you have the freedom to move in this z direction. Then the working distance is basically, if this is your lower part of the objective lens, then the distance from the lower part of the objective lens to the specimen is basically the working distance. You can change this depending upon the requirement which you need to find it in the specimen. Is it fine? What was your doubt? Is your doubt clear or is it there? I didn't got your doubt. Okay. So basically this depth of focus have one formula which is given as 0.2 mm divided by magnification and alpha, where mag is the magnification and alpha is this the convergence angle. So depth of field can be changed by changing the magnification or by changing the alpha. The magnification is changed by varying the strength of scanning coil. Like there is only one way through which you can change the magnification in the SCM, just by changing the area which you are scanning. By changing the lens strength, either condenser or objective, you can't change the magnification in SCM. Only by changing the scanning area. So if you are scanning a smaller area, you will have a higher magnification, whereas if you are scanning a larger area of your specimen, you will have a lower magnification. And how can you change the area of the specimen which you are scanning? That you can change, yeah, that you can change by just changing the strength of the scanning coil. So you can change the magnification not by any lens, just by varying the strength of scanning coils, or you can say just by changing the area which you are scanning. And also the depth of focus can be changed by changing alpha, and alpha is changed Alpha is changes by varying the objective aperture or the working distance. Working distance I already discussed, that as we increase the working distance, your alpha will increase, and as you increase the objective aperture, let me take the pen and show this to you. Suppose these 2 points are your different aperture, so this one has a higher objective aperture, so it will have a higher alpha, whereas this point have a lower smaller objective aperture, so it will have smaller alpha. Alpha is basically what? The convergence angle. So this one will be smaller for smaller objective aperture as compared to the higher objective aperture. So you can change the depth of focus of the specimen of your image by changing the magnification, by changing the strength of scanning coil, or by changing alpha, and alpha can be changed by the objective aperture or by working distance. Are all the concepts clear to everyone? Any doubt in any concept? If no, then we can move to the assignments. I didn't see any raised hand, so I'll move to the assignments part. Since you all have understood the concepts of the SEM until now, so we will together discuss the practice assignment of week 5. Please help with me. Please help to me to answer these questions, and let us see. For the first question says, to obtain higher convergence angle, dash is needed. The convergence angle is the alpha. What is needed to have a higher convergence angle? The first option says the final, the larger final aperture. Final aperture means the objective aperture, because the objective aperture is the one, objective lens is the one which is the final one, which is just above the specimen, and rest all are the condenser lenses. So to obtain higher convergence angle, larger final aperture or lower working distance, or option B, smaller final aperture or higher working distance, or option C, independent of final aperture size and working distance. This we discussed just in the last slide. Can anybody tell me which will be the correct option? I heard some message sound. Option A, higher convergence angle we need.
Option B.
Yeah, option B. Shile. Higher convergence angle. Higher convergence angle. No, option. Why you are saying option B? Sorry. They are talking about. You are able to see the slide, no?
Okay.
They are talking about higher convergence angle. Shailendra is correct. For higher convergence angle, you need to have higher final aperture and lower working distance. That will be having minimum resolution, lower resolution, not minimum, lower resolution. Got it? Your voice is breaking. Are you able to correlate all these things, the convergence angle, aperture size and working distance?
Yes, madam.
Okay. Option A is correct in this case. Option A, for having higher convergence angle, higher final aperture and lower working distance. We just now discussed in this slide, no? The question number 2 says, in SEM, keeping other parameters constant to produce better resolution, probe size needs to be increased or decreased to have a good resolution. Good resolution means the probe size should be, anyone? We have discussed it multiple times in our lectures. Anyone? Shailendra is saying B. The probe size should decrease to produce better resolution. He is very correct. Because the smaller the probe size, the better will be the resolution. So in this case, option B, decreased, is the correct answer. The third question says, which among the following statement is false when working distance is increased in an SEM operation? When working distance is increased, you have to say about the false statement in this case. It gives lesser magnification, it degrades the resolution, it produces larger spot size, it reduces the scan length. Working distance, if we are increasing, it will degrade the resolution. Option B is correct. It will give less magnification. This is also correct, because if we are increasing the working distance, the more area will be scanned, so magnification will be less. Have someone messaged in the chat box? Shailendra is saying option D. Yeah, we are C. And option C says to produce larger spot size. This option is also correct. It will produce a larger spot size and it reduces the scan length. This option is false. So option D is the correct answer for this question. Question number 4 says, as interaction volume increases, the spatial resolution. What will happen to the spatial resolution? It will increase, decrease, or remain the same. Anyone? If we are increasing the interaction volume, then we are getting signal from each time we are getting signal from a larger area. So as a result, the spatial resolution will increase or decrease or remain the same. Someone says option A, that it will increase. Do anyone agree with him? Anyone having any comments in this question about the spatial resolution? Shailendra is saying option B, that it will decrease. Let me tell you, here option B will be the correct answer for this question, that it will decrease. Let me use the pen and explain you. If this is your specimen, your interaction volume is this big, then next time, this is your whole probe. Next time if it will scan here, it will have some overlap, no, of the interaction volumes. This overlap will reduce the resolution. But if you have lower interaction volume like this, and when the beam moves to the next spot, it will have the interaction like this. So here the resolution will be much better. So as the interaction volume increases, like in this case, the spatial resolution will decrease. So option B is the correct answer for this question. Question number 5 says, what information can be obtained from brighter region in back secondary images? It indicates with lower atomic number or higher atomic number. This is the easiest question. Anyone can answer this. Back secondary, yeah?
Option B.
Yeah. Shailendra is also saying option B. Just a second. Yeah. For brighter region, it will have a higher atomic number. So option B is the correct. This is the all things we are discussing about the back secondary electron in our whole class. So if you are able to answer this question, that means you are listening in the class. Then we'll move towards the quiz of this week. The first question says, an electron beam of brightness 10 raised to power 10 uh, is focused to a spot of diameter 100 nanometer at the specimen. What is the current density within the spot? Take the convergence angle to be 0.04 radian. So they are asking what is the current density, and we all know in last class we discussed about the one equation of the brightness. Brightness is basically what? Current density per solid angle. Current density is given by J. C. Current density divided by solid angle. Solid angle is given by pi alpha square. Right? Remember where we broke this current density into the I divided by pi d by 2 whole square. Remember anyone? This is your formula for your brightness, where beta is given as Jc, that is the current density, divided by the solid angle, that is pi alpha square. So in this case we need to calculate the current density, that is Jc. We need to calculate, where the brightness is given as 10 raised to power 10. The alpha is given as 0.04 radians, and pi you already know, which is 3.14. So anyone can calculate and tell me what will be the answer for the current density of this question 1. Anyone having calculator can answer in this question. Shailendra, Rajesh, anyone? You just need to do certain multiplication. Current density will be given by brightness into pi. Brightness is what? 10 raised to power 10. Brightness is, no one is answering. So current density is given as beta brightness, which is 10 raised to power 10, into pi. Pi is 3.14 and convergence angle alpha square. And so 3.14 into 10 raised to power 10 into 0.04 whole square. So that will come about 0.005 into 10 raised to power 10. So if we'll convert it back, it will come to be 5 into 10 raised to power 7. So option A is the correct answer. Did anybody got this answer? Have anybody got option A as the correct answer? Or you are not doing the calculation? This is just simple multiplication. Rajesh, are you there?
Yes, madam.
So did you got this answer?
Yes, madam.
16 into 3. Okay, okay. Okay, okay. If you multiply 3.14, it will come to be 5.02 something. So that will, when you will interchange the power with 10 raised to power 10, it will come as option A, that is 5 into 10 raised to power 7 as the correct answer. Okay, okay then. We'll move to the next question, which says that energy of an Auger peak compared to the equivalent X-ray peak will be higher, lower or same. Anyone can tell answer of this question. This is simple. The Auger electrons have a higher energy or a lower energy as compared to the X-rays. Yeah. So option B is the correct answer. They will have a lower energy. The next question number 3 says, which of the following material is not commonly used as a coating for SEM samples to enhance conductivity and minimize charging effects? So, when the electrons are accumulated on the surface of the specimen, then there is some charging effect occurring, and due to that charging, the electrons get accumulated on the surface of the specimen. As a result, in the image you will see the white things. So the white things is basically the higher contrast. So the higher contrast is basically the one where more electrons are being, so that when the electrons are accumulated on the surface, then you will see the whitish thing in your image. So if your specimen is very charging and it is not stable, then we do some coating of the specimen to prevent the charging of the specimen. So they are asking which of the following material is not used for coating in the SEM to minimize the charging and to enhance the conductivity. Gold is conducting, we can use platinum. Platinum is also conducting, carbon is also conducted. Silicon is the correct option here, because silicon we can't use to enhance the conductivity and minimize the charge effect. This is not used. Generally silicon wafer is used to dropcast the sample to provide the conducting path, but the coating is not done of silicon. It is generally done of the platinum and gold thing. So here option D is the correct answer. The next question says, which parameter has the most significant influence on the depth of field in an SEM image? This statement, according to me, is very vague statement. The accelerating voltage, spot size, working distance, magnification, all are quite unrelated into each other, and you can't say which will be the most significant, which will have the most significant influence on the depth of field. Different terms have their different uh, things. What should I say? You can't really specify that this is the most significant and this is the least significant, because one thing is dependent on the other. Like when you change the working distance, the spot size will automatically change, the magnification will also change, and when you change the accelerating voltage, the interaction volume will change, and as a result your interaction volume will also change. So you can't specify that which has the most significant influence. In my opinion, working distance, changing the working distance will also change the depth of field. Changing the spot size will also change the depth of field. Changing magnification will also change it. So there is not specific answer for this question according to me. Question number 5 says, how reducing the probe size will affect the beam current in the SCM? Can anybody tell me? how we can reduce the probe size. If you are reducing the probe size, how will the current will change? Current will also decrease, increase, or remain the same. This I guess we discussed in the last class, yeah, where we had the ideal system, ideal case. To have the minimum probe size, the beam current should be 0, which is not at all possible. So that using this statement, you can tell that reducing the probe size will affect the beam current by reducing, right? Because the lower the probe size, lower will be the beam current. The next question says, which of the following option is correct? Is this clear to everyone or there is any doubt? Anything in the chat box? Shailendra says option A, reduce. For question number 5, no? Okay, he is correct. The next question is, sorry. The next question says, which of the following option is correct? Secondary electrons, back secondary electrons, X-ray electrons, and auxiliary electrons. X-rays, sorry. Related to what things? Imaging, crystal structural, compositional analysis, detection of very light element. The secondary electrons are used for what purpose? Someone has messaged. Sometimes I get this notification, sometimes I don't. Shailendra says option A. He is absolutely correct. For this question number 6, secondary electrons are used for imaging. Back secondary electrons are used for crystal structure. X-ray electrons are used for compositional analysis, and the auxiliary electrons have very less electron energy and they are used for the detection of very light elements. So according to this, option A will be the correct answer. Question number 7 says, what is the effect of reducing the accelerating voltage in SEM imaging of non-conductive samples? So if the sample is non-conductive, then there will be, firstly there will be charging of the specimen. So if you are decreasing the accelerating voltage, that means you are providing less energy. Less accelerating voltage means less. Has someone answers? No. Okay, let me explain. Option B, that is decreasing charge effects. Yes, he is correct, because if you are reducing the accelerating voltage, the less amount of current is coming in the specimen. As a result, there will be less amount of charging. There will be charging in the non-conductive samples until and unless you have coated it and provided the free path of the path for the electrons to be grounded. So if you are reducing the accelerating voltage in non-conductive sample, it will decrease the charging effects. So option B is the correct answer. Where is the pen? Question number D says, when adjusting the condenser's currents in SCM, what is the relationship between the condenser and final probe current? They are directly proportional, inversely proportional, no relation, relationship is non-linear. Any guesses? Because when we are changing the current in the condenser lens, no, the final probe will be directly proportional, because if we are changing the current in the condenser, then its focal length will be small. If we are increasing the current, as a result it will focus here only. But if we have a higher current, it will focus here. Lower current, sorry, my bad. Let me make it clear to you. Let me change the color. So this one is at higher current. If the current is increased in the condenser length, the probe the it is focused here, but if the current is lower, focal length will be higher, it will focus at a higher distance. As a result, the final probe size, by when I am increasing the current, the final probe size is also increasing. So it is directly proportional. So option B is the correct answer for this question. So question number 9 says, for thermionic emission, which of the following factors affect the efficiency of electron emission from a material? Thermionic emission. Thermionic emissions, do you remember we discussed in the last class that there are different electron sources? The Schottky, the someone has messaged. Let me check. Shailendra says option C. Option C is what? The material's work function. Yeah, you are absolutely correct. We discussed this in the last lecture, I remember. Different, like we use tungsten filament, the lab 6 filament, these have different values of the work function, and depending upon the work function, the the energy is supplied to the material, and when the energy is being higher than the work function, then the electrons are being generated from this source, that is the gun. As a result, the answer for this question, that which factors will affect the efficiency of electron emission from a material, will be the material's work function. That is option C is the correct answer. Question number 10, the last question, says, if the coefficient of a spherical aberration is increased by 1%, what could be the percentage change in the minimum probe size? Last class we discussed about all the aberrations, the spherical, chromatic, astigmatism and all. And there we found out that after solving that all big equation of d probe square, like it was written as dp square is given by, remember, diameter of size of probe due to Gaussian ka square plus probe size due to spherical aberrations ka square plus d due to chromatic plus d due to diffraction limitation, that is small d ka square. So this was basically the size of probe is given by the Gaussian, spherical, chromatic and diffraction limitation. So using this, when we will do the final calculation, I remember we wrote one formula which shows that the minimum probe size d minimum is given by k lambda to the power 3 by 4 and the spherical aberration coefficient to the power, that is CS, to the power 1 by 4. The question says, what is the, if the coefficient of spherical aberration, that is this CS, is increased by 1%. What could be the percentage change in the minimum probe size? Can anyone answer this question using this formula? If CS is changed by 1% and that to the power 1 by 4 is related to the minimum probe size, then how the D minimum will be changed? I'll keep this. Anyone? Someone who messaged. Shalinder Tiwari says B 30. Anyone else? Shalinder, can you please retry using this formula that D minimum is directly proportional to CS to the power 1 by 4? It is related to the power 1 by 4. So if it is increased by 1 by 4, 1%, then 1% ki power 1 by 4 will be how much?
Point 25.
Please don't say 0.25. After point you don't say 25. You should say 25. 30. 0.30, not 0.30. So its answer is correct. It's 0.25. So because CS, here the CS is changed by only 1%, and it is related to D minimum to the power 1 by 4. So the 1% ka power 1 by 4 will be 0.25%. No? Shirendra, do you got it? The answer will be option A.
If you take 0.01, 1% is 0.01 to the power 0.25.
They have also asked the question answer also in percentage, so you don't need to convert 1% to 0.01, no?
Oh, I see. Okay.
So if it is 1%, then 1 to the power 1 by 4. It will, the basically you can directly correlate, no? You even don't need calculator for this one. Got it?
Yeah, got it.
Okay. So with this, the assignment of this week is over. And if you have any doubt in the SCM part, do let me know. Otherwise, I'll upload all the lecture link as well as the presentation in the provided link so that you can have it access of this later on. If there is any doubt, do let me know. Any comments on how I can improve my teaching, anything is there, do let me know.
Sir, second question, can you explain one more time?
Which one?
Second one.
Second one for which?
Second question.
Second one of the quiz or the assignment?
Quiz.
Okay, let me check.
Quiz, ma'am.
Second question of the quiz is very simple. This one only you are asking. The energy peak of an Auger. The energy of. Can you please mute yourself? I am not able to speak properly. Yeah. So the energy of an Auger peak compared to the equivalent X-ray peak will be what? I always told you in this slides also. The Auger electrons have the minimum energy, very low energy. So as compared to the X-ray also, it will have a lower energy only. So in this case, option B is the correct answer. What's the doubt in this? Is it clear?
Yes, ma'am. Okay, ma'am.
Okay.
Yes, ma'am.
Okay. Any doubts? Any comments? Are you all there? If you have any doubt, please let me know. Sunisha, are you there? Do you have any doubt? If you have any doubt, you can ask, otherwise, you can leave the meeting. I'll cancel this meeting since I'm not hearing anything from you.